Hello, good morning. So we continue from where we stopped last week. So this is another form of the binary eutectic system, right? Are we together? Vladimir.
Yes, we are.
System you can see here is aluminium and silicon. Silicon, on the other hand, is hard and brittle. It has a cubic crystal structure. Aluminium is FCC crystal structure. The two have limited solubility. Here it means silicon is soluble only in small amount. Here, can you see? So here is aluminium 100%, then we begin to add silicon. It's not running up to 100% because the only important portion is up to 18 to 19%. And silicon is one of the few elements that expand on solidification, right? Therefore, hypereutectic aluminum silicon alloys have 12% silicon, does not shrink. Portion, we know anything after this is hyper. Before it's eutectic is hypo. Right? The initial phase diagram is brittle in nature, right? Up to is 11.6% the eutectic. But when you dope it with sodium, you have this. So you can see this brittleness has become something like a circle. Can you see? These dark spots, they are the silicon. See, it has turned to what? When you dope with silicon, it has turned to like circle, and this makes it very ductile. So sodium alters the compositional and temperature of the eutectic point. So this is what it means. And so you have a much improved with more ductility. So this is the property, initial property without adding sodium. This is the percentage elongation, and this is the unmodified. Unmodified you can see, and unmodified. But as you add sodium, you can see the strength has increased significantly. The initial, this is the unmodified strength, and this is the final modified what strength. See, the strength of aluminum is about 70 something or 80, right? Can you see my mouse?
Yes, sir.
You look at this tensile strength. This is in kilopounds per square inch, so it's about 80 megapascal. But when you increase, when you add silicon, you can see both unmodified and modified are increasing. Can you see? As you add 5% silicon, the strength is increasing. As you add 10% silicon, right? Adding silicon to aluminum increases significantly the mechanical property. But when you modify it with sodium, the strength significantly what? Increased. Up to around close to 200. So next is another type of the binary eutectic system. In this case, we are looking at copper and zinc. So you can see within all this region, the zinc is soluble in what? In copper. So there is what we call peritectic. And what does peritectic mean? So there are four intermediate phases, beta, alpha, and they are product of peritectic reaction. These phases do not have fixed composition. You can see they are not fixed because look at beta here. You can see this double line. So it can flow, right? They can overlap. So let me explain what peritectic reaction means. Meanwhile, I will come back to that. So here you can see when you add zinc to copper, you can see the strength is increasing. Can you see significantly? This is tensile strength from the right. Can you see? So the strength of pure copper is about what? About 320, right? Or 350. So as you add 10% zinc, you can see the strength increasing. Can you see the curve? I hope you can see the curve clearly. Up to about 30%. When you have zinc 30%, you can see where it has a maximum. Or up to 40%, but the elongation is up to 30%. Then it begins to what? Go down. Okay. So here, as I said earlier, this is an example of peritectic reaction. It's transformation from solid plus liquid to what? To another solid. Can you see? But not at constant composition. Can you see it? Or transformation from solid to solid plus liquid. You know, the air is liquid, but at what? Variable composition. But eutectic is at what? Constant composition. Can you see it's a straight line directly on this? Can you see the line? The shaded line. So the eutectic is either from liquid to solid, two solids, or from two solids when you hit to what? Liquid. While peritectic is from liquid plus solid plus liquid to a new solid. It's not at a constant what? Composition. You can see it's slanting, while this is at constant particular composition. So as I said earlier, you can see when you add zinc, you can see the strength is increasing and the elongation is also increasing. Can you see? Zinc to copper. So similarly here, that of tin, we have also peritectic. You can see alpha plus liquid to what? To beta. Right? Can you see this region? So this is all about this. And okay, you can see the strength of the alloy can increase significantly. The strength of copper, as we see here, is about 320. But when you add tin, you can have up to what? 690. Or even 586 or to 690, right? So you can see the importance of alloy. So next we look at the ion carbon phase diagram. So here you see we have the alpha region, which is only solid, a solid solution. It means the carbon in this small region alpha is soluble, isn't it? So as you move from this region to here, the carbon is no more soluble, so it will appear as what? Some carbon atom is soluble in alpha, but then anything above 0.022 will not be soluble in alpha. So it will come out as what? Cementite, iron carbide, right? And so here we have solid solution austenite, which is gamma. So within here, all the carbon in this region is what? Is soluble. Then when you exceed 2.41% carbon, it becomes what? Insoluble. So you have an additional phase, which is what? Cementite. Can you see? And so this is the eutectic transformation from liquid to solid. That's two solids, which is cementite plus austenite, right? And when you heat, you have liquid. Region we are going to be looking at this. This is one of the most important regions. We call it eutectoid. Eutectoid is transformation from what? One solid to two solids. Let me add it here. This is already is given here, peritectic. And then finally, this is similar. This is eutectoid. Eutectoid is transformation. This is the movement is at constant from a solid austenite to two different solids, which is ferrite plus what? Cementite. And this occurs at 0.076. Eutectoid. We call this eutectoid. So next we are going to study this region and see how important it is. You can see the advantage of alloying, adding carbon to what? To iron. You can see the strength significantly increasing. Right? Strength and hardness significantly increasing. You have eutectoid, alloyed, and microstructure here. So we are going to be looking at this. So this is an important region. We are going to be looking at the eutectoid. I just showed you. We are going to be, because it's important in heat treatment of steel. Because in eutectoid, you have transformation from solid to two solids, right? From austenite to ferrite plus cementite. And this is exactly the region from austenite to ferrite plus what? So when you cool from austenite, you exactly have this. You have ferrite alpha plus cementite. So this is the only region you have this. So when you move leftward at 0.7, and it happens at what? 0.76. So when you move leftward, it's hypo eutectoid, and when you move rightward, it's hyper eutectoid, right? So this is the only place you have this. And eutectoid is alpha. You can see like donut, like sausages, right? And then the background there is the cementite. And so this is the eutectoid. It's called also perlite. We call it perlite. So this is hypo eutectoid. It means left of the eutectoid. In this case, when you cool from austenite, you will have, it begins to change shape. You have austenite plus what? Ferrite. And then when you cool down, you have finally this. So here it's a combination of what? We have combination of perlite, which is the alpha plus cementite, and then plus what? Additional ferrite. Perlite is this donut shape at the background. And then the additional, can you see this like a bigger T branch? It's called the what? So you have two types of alpha. This alpha that is big, and then we have the other alpha in the eutectoid, right? Eutectoid is the same as the perlite. So when you are doing your calculation, we are coming to that. And when you are rightward, you won't have ferrite, you will have additional cementite, right? So you can see this. Can you see my mouse? So this is the additional cementite. Can you see it? We call it the projectile cementite. And then we already have the perlite, which is what? Cementite plus ferrite. Ferrite plus cementite. So this is it. So when we do the calculation now, so let's look at this example. It's going to be, so now let's look at this question now. Solution number 4, and that's how we start our, for a 99.65% iron and 0.35% carbon at a temperature just below the eutectoid. So determine the following. The fraction of the total ferrite. Determine the total ferrite. Look at the question. Determine the total ferrite and cementite. So the question is asking about ferrite and cementite, isn't it? It means you have to locate their boundaries, right? So look at it. This is the boundary of what? Ferrite. And this is the boundary of what? Cementite, right? Boundary of cementite is 6.7. Is it clear? Yes, sir. Did the question talk of eutectoid? There is no talk of eutectoid, isn't it? So we shall not bother about its boundary. There is no eutectoid. So in this case, we are talking of the total what? Ferrite and cementite. And this region, you know, is alpha plus cementite, right? And our alpha is our ferrite. So you locate the place. What's the place? 99.65, somewhere here, isn't it? And so we locate the temperature. This is the composition. What's the temperature? It says just below the eutectoid. What is the eutectoid temperature? It's 723, right? So just this is the eutectoid temperature, is it not? This horizontal red line.
Yes,
so just below, just draw any line below it. So this is the temperature. So this is your point. Then you draw a tie line, isn't it? To connect the two boundaries. So this is the first boundary because we are looking at the total. This is the cementite boundary, 6.7, and this is the ferrite boundary, 0.022. So we look at this total and then we'll be able to calculate our what? Our ferrite and cementite, isn't it? And so you give this distance t and this distance x. Remember, when you're calculating ferrite, you don't take the t, you take the opposite, which is x, right?
yes,
X over the total, and the total is t plus x, total distance. And you know, you come and get your estimate your x here. Your x is 6.7 minus what? C naught. And your C naught is given as 0.35, isn't it? Your C naught is given as 0.35. And then you get your total, 6.7 minus 0.022. That's the total t plus x. And you get 95%. The moment you get the first one, you know the other one is going to be 5%, but you can prove it, right? So when you are calculating that of cement, this cementite boundary, so you won't take the x, you take the t over the total, t plus x, right? And you can see you're able to get 5%. So the second question now, you have to look at the boundary for each question. The second question now says, ask us what? To calculate the fractions of the proeutectoid, ferrite, and perlite. In this case, we are looking at what? Hypo, right? In this case, it is left. Where is the perlite? The perlite region is this, 0.76, right? So it means we have two boundaries. This boundary 0.76 and what? And ferrite. Because the question asks what? So there are two different types of ferrite. There is proeutectoid ferrite, which is this, which is the bigger ferrite. Can you see? Like a tree. Can you see my mouse? This one that looks like a tree leaf or branch. And then there's also the one in the perlite. The perlite is a combination of alpha plus, it's a combination of ferrite plus cementite. So in this case, you are going to find the combination of this alpha plus cementite, which is 1 perlite, and then this one here that stands out, proeutectoid ferrite. So you locate the boundary. So this is the boundary of the perlite, and that is the boundary of the what? A proeutectoid ferrite. So it's the same composition, isn't it? 0.35. So you know your what? So for the perlite, you look at this perlite, you will pick which one? Are you going to pick U? It's going to be the opposite, T all over what? Total. And for proeutectoid ferrite, you are going to pick what? Yes, you won't take what is adjacent, you take the U over. So this is exactly what you did. U over the total, T plus U, and T over the total. Then lastly, this question asks us to find what? Fraction of the eutectoid ferrite. You know, it means there are two types of ferrite. There is ferrite in the, let's assume our ferrite is green, right? So you can see this bigger green is called the proeutectoid ferrite. And then this one in between that makes this, they are the other greens. So there are two types of this perlite. We have this one, the bigger one. Can you see them? There are three, isn't it? We call them proeutectoid ferrite. And then there's also ferrite here within this cementite. You know, we call this color cementite, isn't it? And then as this cementite is there, it's an alternate layer of cementite and what? Ferrite. We call it eutectoid. So the ferrite, if you look at it very well from this part, there are two types of ferrite, isn't it? The big ferrite, which is called proeutectoid ferrite, and then the ferrite in the perlite. And then we also have this. There are two types of ferrite. This ferrite now is, this part is called what? Perlite. And perlite also has ferrite, is alpha plus cementite. The alpha is the green in there, right? So it means the total ferrite is going to be what? The big proeutectoid ferrite plus eutectoid. The small one here is the one in the eutectoid. We call it this eutectoid ferrite. So remember in our question 2, where we determine the perlite and the bigger ferrite. So since we know the total percentage of the, in the first question we determine the total percentage of the ferrite, right? Which is 95%.
yes, sir.
In the second question we determine the other ferrite, which is the big one. This big CP, which is what? 56%, right? So the other ferrite, you know, we can be able to determine. So the total ferrite is equal to protected ferrite plus detected ferrite. So first question will determine the total ferrite. Second question will determine the big ferrite, right? So for us to find the other ferrite in the perlite or in the eutectoid is we can just do this. Total is 95. This is what we are asked to find, and so we can determine it. Or the second one, since we know the second question will determine the total perlite. The total perlite is what? 44%, right? I know perlite is equal to what? Perlite is equal to ferrite plus cementite, isn't it? Perlite is equal to ferrite plus what? Detected ferrite plus cementite. So in the first question, we determine the total cementite, which is 5%, right? And in the second question, so all what we don't know, we know the total perlite is 44%, and we know the cementite from the first question is only 5%. So we can determine the ferrite in the perlite. So in this case, we can determine it 95. So we can do two ways, 39%, and to give exactly the same. So we've come to the end of our lecture. Now we